Let's see if I'm live. I always have to check. Because sometimes I don't know. Alright. Videos live. Yellow. Okay, looks live. See if I'm live. I always have to check. Alright, that looks good. Let's get chat. So now I have to go back to my channel. Live, pop out chat. Boom. That looks alright to me. Don't have the link to the last co-create I had discussing this. I guess that's good because it means I just have to remind people. What's up, Arad? We can also do something else because the plan, I mean, I'll do this at some point, but we can talk about something else first. The plan was me to go over if this is true, it's left and right exact. Although I feel like you should already just know that. But maybe what you don't know is that if it's exact, this implies that rep G is semi-simple. I already showed this for the last stream I did. I showed this for finite groups where P doesn't divide the order, and for compact Lie groups. The funny thing is those have the same proof too. Or you can also talk about whatever's on your mind. Or I was reading some stuff that was interesting. We could try to figure out some stuff about differential Galois theory. I was reading just a bulletin about it the other day. Or do you want to hear about I wrote a blog post arguing that we're missing a linear algebra course for pure mathematics. That essentially there are no linear algebra courses for pure mathematics. The language of linear algebra and pure math is just not represented in any courses. Let me see. I'm also gonna add you as a moderator. Once blue, always blue. The once and forever blue. So let's see. Because you're here. Do you know about higher semi-additivity? It's a generalization like in KN local homotopy theory. All limits and co-limits coincide, not just co-invariance. Very neat. No, I do not. 3 blue, 1 blue. No, I do not. Higher semi-additivity. All limits, not just co-invariance. Well, all limits and co-limits coinciding is quite a lot. I mean, I know, additive, where you have A times B coincide with A. That seems like quite a lot. Do you have an example of a category like this? Because that actually seems very odd for all limits and so if I have a diagram D, lim D equals colim D for all of them? That seems like maybe that's too much for me. Because, I'm just thinking, yeah, what category would do that you would use? Limits and co-limits indexed by finite groupoids in an appropriate sense. Oh. Well, can you give an example? Because I still don't know what you mean. Something beyond, I guess this. Indexed by finite groupoids. Is this a limit or a co-limit? This is, invariance is really, these are both adjoint functors. Rho G is a left adjoint and rho underscore G is a right adjoint for, going from rep G to just forgetful functors to vector spaces over K. Category of K then local spectra is an example. Okay, I wouldn't know that. At some point, the furthest I got in homotopy theory is, I guess, a definition of spectra. But and what they show the example is sphere spectrum, and you clap your hands. You know, the iterated suspensions. Yo, Dylan Hafner, how are you doing? Invariance is the limit over all G-shaped diagram, and co-invariance is the co-limit. So if I have a G-shaped diagram, is the limit over all G-shaped diagrams? Well, let's see if I can see why that is. Let's see if I can draw a pretty picture. So if I have, let's just do it in this example. Why not? We have rho. And then a G-shaped diagram. I mean, we have all of these, you know, this is just a G action. A G-shaped diagram on rho. All of our elements giving these isomorphisms, G to G. So variance is the limit. Is the limit, or would it be the co-limit? Whatever, let's see. Over the G-shaped diagram. Oh, I think I can see what you mean. Because you have rho G. Oh, yeah, no, I'm picking up what you're putting down. Yes, that this is commutative. And yes, it would be universal. Okay, so I see it. It is a limit. And then covariance would be the exact same thing you're mapping out of it. Okay, you've convinced me. Very good, Arad. Okay, I see it. So higher semi-additivity. Also, Dylan, the plan for today. Plan for today. 1. Talk about random bullshit. That's what we're doing now. 2. Show this, if this holds in like a category where you're doing representation theory, then the representations of G split completely. And the talk about random bullshit thing is basically if you have anything you want to talk about, we can talk about that random bullshit. Right now, Rod's telling me about, maybe I should just Google it. What is it called? Higher semi-additivity? Higher semi-additivity. Let's see what we get. Oh, Arad, you have the power of blue, so if you want to link something that you, I don't know, endorse, you can. You have the power. What other stuff? What's a random thing I want to learn? We could also put differential Galois theory on there. Theory. It's semi-additivity. Oh no, you you went with NLab? Resident NLab hater here. No, where's the AMS bulletin I had? Oh, we could also just watch a talk. Introduction to differential Galois theory. That could be fun. Though it's a little long. Also, I don't know if you guys hear it. Well, let's see.
Been introduced yet?
Do you hear it?
Been introduced yet? Not yet. Okay, great. Thank you.
Yeah, I'll open the link. Infinity measure says n semi-additive coincide with their infinity, 1 limits over m finite spaces. What are those? Connected space is m finite. If x is m trillion, pi k is finite for all k. Oh, is this like a sort of... Is it kind of like a... Is this like a notion like a higher groupoid type of thing? Like, if we have this, it's kind of like we're doing one groups. But how does that get to semi-additivity? Well, let me get AirPods in so you don't hear the audio twice, so it doesn't sound terrible. Hopefully it connects. Spaces equal infinity groupoids. Okay. Yeah, I can get behind that somewhat. You have your groupoid. You have your 2 bits of equivalence. Imagine I'm making a solid sphere. Inside you have your infinisphere bits. Differential Galois theory. Is that what we want to watch? Actually, I think I have a playlist of stuff that I was thinking of watching. Watch later.
Good afternoon.
Let's see if there's anything here. Pierre Deline. Let's do this. And then connect things. Why is it not finding this? There's degrees of freedom. Double modular arithmetic. Oh, double modular arithmetic is something that you use in a bunch of algorithms applications. Anime math. Non-standard analysis might be a good one to go with. I kind of want to learn some stuff with non-standard analysis. What else is here? Kay's video? Should we react to one of Chris's videos? Ampere Serre. Could even do this one.
Good afternoon.
What is the Hodge conjecture? I feel like people are interested in that. Why is the Bluetooth not working for me though? You know, I might reverse the order, Arad, if you're okay with it. I might quickly finish up the proof of semi-simpleness of these representations, and then either react to something or talk about various spectra stuff. Because I kind of want to do that, and I feel like if I do something else, I'm going to forget about it. And also the AirPods are not working with me. So they don't want you to have better audio. You can blame Apple. But yeah. So random bullshit. We're going to come back. We're going to come back to random bullshit after. But just to remind people, all right, semi-simple representations. This is, how do you spell this? Maschke's theorem and compact Lie groups are semi-simple, which just means that if I have representations of these, finite dimensional representations, they split into irreducible representations, meaning they're very nice. You don't have these annoying blocks that prevent nice splitting. The Maschke's theorem case is precisely the case where G is a finite group and you are working over a field of characteristic not dividing G. And the reason you need this is basically because you end up in the proof of this dividing by G. And so to divide by G, you don't want the size of G in your field to be 0. The other case is G is a compact Lie group. So something like S1, I don't know, SON. Is SON compact? Think about it. It's got a determinant. Yes, I think the O of n, well, if SON's compact, ON's definitely compact. So, I believe all of these are compact. I could be wrong. Actually, U of n, I would guess, is not compact. Maybe I'll do a Google compact Lie groups. You could just do list. So you want to yeah, tori are definitely unitary. Okay, unitary is u dagger u of n. All of these can be proved with Heim-Borel. So really, I should give this to you guys as an exercise to show that these are compact. But let's get back to it. You have a compact Lie group. We can do a very similar proof above, that rho g is isomorphic to rho g. So I did this last stream, which I'll link, but we have these two functors from rep g just to vector spaces, essentially, over your base field. And rho g is exactly, gives you the subvector space of v, if v is your base vector space of everything that is fixed by everything that's a fixed point. So these are your fixed points, your invariants. And your co-invariants have a similar property. It's kind of the mirror image. Actually, if you didn't skip to this part in the stream and you go back, you can see that Arad showed me that the invariants and covariants are the limit lying above and co-limit lying below, respectively, of this diagram, which is just rho, with all the isomorphisms that you get from your group action. And so this is V mod W, where W is the subspace of V. W is a subspace of V, precisely given by V in V. No. It's G C dot V minus V, for V and V. So you're essentially, in this one, you're finding the vectors which are fixed by G. And here you're killing the translations. So both of these give a sort of fixed nature. And we have this map, rho G to V to rho underscore G. Oh. And you can define a symmetrization map that really goes from V to rho G, but because it fixes the subspace W, it induces a map here, your symmetrization map, which I'll call, in all cases, sim underscore G. And the symmetrization map, should it exist, will show that these two functors are indeed isomorphic. That was in the last stream. The step now is that, okay, we show these two functors are isomorphic. How does that let you prove these two things? Well, there's two facts left to prove. One, if rho G, well, I guess there's three facts, is isomorphic, then this is an exact functor, which is a good thing to know. It's very useful. The next thing to know is that if I take this, if I have two representations, rho 1, rho 2, we don't have Hom, unfortunate. Aw. Text Hom. If I have the Hom between these two representations, this is isomorphic to rho dual tensor, rho 1 dual. Rho 1 dual tensor rho 2. Is that right? Yes, that's right. No budget for Hom. Yeah, that's true. Well, the funny thing is this is an open source thing, and it's hosted by someone I know. I'm worried about it escaping containment and too many people using it, and so either getting slow or essentially MIT taking it down. And if that happens, I'll have to self-host. But if I self-host, I could custom put in all of the math commands that I want to use. And so maybe at some point I will self-host and it'll have all of the commands that I want, which would be nice. So Maybe that would be a hidden thing. So this is also a G representation. And the important thing to know is that this is a G representation. And it's the K morphisms is a G representation, not necessarily the G representations. But I'm going to call this representation, I don't know, capital rho? Is that a thing? It does not like that. We're going to call it H. Big H. Yeah. H to the G is canonically isomorphic to the G Hom. Rho 1. Oh, no, I don't want a dual there. Rho 2. Boom. So then, once we have these two facts, we can combine them. And we can note that using a clever trick using Hom, you can split any short exact sequence of G representations, and then you can pass from that splitting of vector spaces, because short exact sequences of finite dimensional vector spaces always split. That's what the rank nullity theorem is. That's how you prove it. You can pass to the Hom and the G representations, because exactly that this is an exact functor, it will show you that you also get a splitting at the level of G representations, which is all you need to show that you can decompose into irreducible functors, because you can just keep splitting and splitting and splitting. I might have to take some meds soon. Maybe I can finish this proof first. But yes, then we will use these to show splittings essentially lift to G splittings. And the funny thing is, you might see a proof of Maschke's theorem or that compact Lie groups are semi-simple, and you might see like some equation where you take a morphism and you take this symmetrization where you do the sum of the G's and 1 over G or some integral. And you might ask yourself, is that related to this? And these two things are actually the same proof. Because if you follow these isomorphisms, what you will get is that it's the same type of map of how you turn a vector space splitting into into exactly what you want, which is a G representation splitting. So let's go one by one, and let's just prove these 3 steps. So first, rho G simic rho G is an exact functor. This is kind of easy, because in this case, and all we need to show is that preserves injections and surjections. Well, how do we do that? Rho G preserves injections. Can I draw a nice diagram here? Say we have rho. Do I have hook right arrow? And to rho prime? I do! Great. Then I know that rho prime of G is just, give me a second. Then I have exactly what I want. Well, I don't want this T here. What is going on? I have exactly what I want because I can make a cute little diagram here. That when I take the fixed points of rho, this is just the fixed points within rho prime. And so all of these are just, sub-representations. These are injections, and this is an injection. Essentially the same story holds where rho G preserves surjections. But I'll do it, I guess, with more formulaically. So let's say rho now surjects. Oh, how do you do a surject? 2-head right arrow. Cool. Let's say we have a surjection of G representations. We want to show that the coinvariance surjects. Well, it's not so difficult. Say I have V in rho prime underscore G. Oh, I don't want that backslash. Yeah, rho prime g. Well, this v will lift to some element here in rho prime, which, because it's the surjection, will lift to some v tilde here in rho. And then because of functoriality, that v tilde will map to something in rho underscore g. And because this is functorial, and I've just done lifting over these maps, whatever this v tilde maps to will map to the original v that I picked inside of rho prime. And so, budget for hook right arrow. And because we map rho g, picked v arbitrarily, this shows that surjections are preserved. Okay, one of these functors preserves injections, one preserves surjections, but they're isomorphic, so therefore it's an exact functor. And so we can celebrate. Yay, it's an exact functor. All right, step 2. Where is step 2? Oh, it's over here. Oh, yes, this is an important step. We can show it in a couple of ways, but... No, it's not so hard. Okay, let's do this. Do I want to show it? I guess I could just cheat and say something, but no, I'll do it in the rho dual type of way. So, say, we have rho, we have our rho prime, right? And we're working with the linear maps. So say we have some, I don't know, some phi that goes from rho to rho prime. Nice. Some k linear map. The question is, what is g phi? And in essence, I could just tell you that g phi is defined to be this. G phi, I'm writing this with a trackpad. Isn't it beautiful? G phi g inverse. And this is true. But I'll also show it that this comes from, well, I don't know if comes from is the right way to put it. But this can also be realized by the fact that these are isomorphic as representations. Because if I have a representation rho, I can get a representation on rho dual, where exactly if I have an element of rho dual, which I'll also call phi, then g c dot phi is equal to phi of g inverse. You're wondering why we do the g inverse? In essence, it's to keep it so that we have we still have a left action. But I guess in the opposite, it would mess things up. If we have a right action, then the g inverse, you can't escape the g inverse. Because if you wanted right actions, the g inverse would find itself into your regular representations. And so the g inverse kind of always is with you. But then how do you do if I have the tensor product of two things? What is g acting on it? So let's say I have g c dot some element of the tensor product, which would look like phi, which will be some dual map, times some v prime. Well, this will just be equal to phi of g inverse O times g v prime. And if you decompose what this means, the map represented by phi v prime is precisely the map where you go from v to phi of v times v prime. And so what do you get when you do all of this? Well, you precompose with g inverse. So if you add in a g inverse here, and then you post-compose with g, and so you add in a g here. And that's exactly how I defined it beautifully, the action on g. I guess I wrote var phi there, so G var phi equals G var phi G inverse. Okay. So we went through all this stuff to give, I guess, an argument, not a proof, because really this is by definition. So I wouldn't really call this a proof, but I'm just showing, I guess it's a proof that these two things coincide. So what are the G fixed points of this? Well, the G fixed points are exactly the linear maps such that for all G, I'll write it out, for all G, phi equals G phi G inverse. G inverse. Okay, well, what does that mean? It means that this is, you can move the G, you can delete the G here, take it away, and you can put it over here. And so it's G inverse phi equals phi G inverse. It means G commutes with phi, and that's exactly what it means to be a G map. So it's almost tautological that the G fixed points of the Hom set is precisely the G maps. But now we put it all together. Step 3. We'll make it a little bigger. Putting it all together. Okay. So how do we show that if I have some representation rho, that it splits into a bunch of irreducible representations? Well, all we have to show is that if there is a subrepresentation, some rho 1, a subrepresentation of rho, that we can split this into, some rho 1 comma rho 2, where it's the sum of rho 1 and rho 2, and then you can induct down by dimension, because the dimensions here and here will be smaller. This is finite dimensional. So as long as we can show that if rho is not irreducible, then we can split it cleanly. By induction, we can split it cleanly into a bunch of irreducibles. So let's prove that. Well, what do we have? Say we have some subrepresentation of rho. Well, that means we also will get 2 head right arrow. A quotient, we can take rho mod rho 1, and we can form this short exact sequence. 0, right arrow, this to this. And we know from the rank nullity theorem that we have, maybe I'll just prove this again, that when does this thing split into, what you want? Let's call this pi for projection. Well, it splits exactly if there is some linear map here, I, such that pi composed with I, is equal to, this is, do we have the identity? No, we don't. Text identity, the identity on rho 2. That if, I'm just going to write this all a little cleaner, because this is disgusting. If pi circ I equals this. So this is the condition we're looking for, and this holds. We can find a vector space map I, but we don't know that it's a G map. Well, how can we show it's a G map? Well, the interesting thing is that pi gives us a map on the level of Hom sets. What is the map it gives? It gives it by post-composition. We have this text Hom underscore k, rho comma rho, and we have a map given by post-composition with pi, so circ pi, to text Hom, I can't type, I guess, underscore k of rho comma rho 2. Okay, well, what does this give us? We have Hom rho comma rho, and we have ham rho comma rho 2. Is this what we want? Let me think for a second. Because we want to get to id rho 2. I don't think this is what we want. Maybe we want rho 2, rho 2. Gonna have to think about the splitting that we want. Because is this surjective? We post-compose with pi, we get... It is surjective. But we want to say something about the element id rho 2 being liftable. Well, let's think. Let's see if we can figure out the proof. Ham k. Maybe we want to start with this. If we have rho 2 to rho 2, and we have the identity element here, we want to show that that lifts to something rho 2 to rho. Ah, I see what we want. So we have ham 2, rho 2. Ah, yes, this is what we want. Okay, so somewhat similar. This is not what we want. We're just going to delete that. We're back in business. We want to look at these ham sets. Why does it not like this? Oh, because I did that. So we have the space rho 2 comma rho, and we want to consider circ pi. Consider this. Let's make this smaller. All right, now we're in business. Now we're talking about what I want to be talking about. So ham k rho 2 comma rho, that's exactly our candidate I. These are maps from rho 2 to rho. Cool. And we have post composition, and that gives us the composition pi I. And we want to lift the identity map. Well, one thing is we know that for any pi, or for this given pi, this map is surjective. And the reason it is that if pi is surjective as a vector space, every surjection splits. And every surjection splitting is the exact same thing as saying that this morphism here to here, is a surjection. Because it means we can lift anything here, including, id rho 2. Well, if you can lift id rho 2, you can post-compose with anything. So, like, if this splits, it means you can lift id rho 2 to something, id rho 2, id rho 2 tilde, that maps to it. From ham rho 2 to rho. I'm trying to see if I believe myself here that this is a surjection. Because if pi surjects to that, and I have a map rho 2 to rho 2, then I can precompose with rho 2. Yes. Okay, I do believe this. Okay. Say I have an element psi on the right-hand side. An arbitrary element. And say id rho 2 lifts here. Then psi... actually, I want to precompose. If I precompose, which means doing this, because we write composition the wrong way, id rho 2 composed with psi will map to psi. So this statement is basically saying that if a surjection is splittable, if you can lift the identity, then this is a surjection on the level of ham sets. Okay, cool. So we know this is a surjection on the level of ham sets. Now we can apply our exact functor. Apply the functor g. Well, that will tell us that this same map, which I'm actually just going to copy, going to go here, is still a surjection at the level of g sets. Because g is an exact functor. If this is a surjection, this will be a surjection. Which means that we can lift id rho 2, id row 2. Oh yeah, you still can't. You have to do text id. Text id row 2. Oh, my head's all low. Id row 2. I can't type for anything. You can lift it to something such that id row 2 composed with pi, or whatever you lift it to, pi composed with I, is equal to exactly what you want, id row 2. So that means when you have this short exact sequence, which is split, you can take the G invariance, which by doing this you G average it, and you can find a splitting at the level of G maps, which tells you then that row is isomorphic to row 1 O plus row 2. I want to review this a little bit because I was getting things, I was thinking on the fly to remember how to prove this. But the real point is that splittings correspond to this being surjective. And if we have this exact functor, it stays surjective. And the reason it corresponds to surjectivity is because being able to lift id is the same as surjectivity. And then if we can, then it just follows from the rank nullity theorem. You split as a vector space, you average it out, and then it splits as a representation. And so I would say this proof, even though you can do an equivalent of this kind of many-step proof by just writing a formula and checking some relations, this proof reveals, maybe in the style of the rising sea that Grothendieck talks about, you know, what sort of pieces are at play. You know, the exactness of passing to symmetry becomes sort of intimately related to how taking an invariance functor gives you G maps. And so given all of that, that concludes the proof in step 2 of the stream, which was show that if we have this isomorphism, G splits completely. All what is it? Linked to the first stream where I do the first part of this proof, where I just show this for Lie groups and for finite groups. But anyways, I'm done with that. So now I'm gonna check if anyone's here and they want to talk about anything. If not, I'm probably gonna head out. It says 1 watching. I wonder if that's me. Arad, you still here? You want to talk about something? Otherwise, I'm gonna head out. I got my proof done. It was fun. SAS Rochester. Differential Galois theory. Well, it looks like it's just me, so proof done. Heading out.